have some. Where did that sounds good. I need that.
So everyone, I'll introduce Dr. Hofmann here while we're waiting. So Katja here is a researcher at the Machine Intelligence and Perception Group at Microsoft Research Cambridge. Super happy to have been introduced to her by Mark Rydell earlier this year. Before joining Microsoft Research, she completed her PhD in computer science as part of the ILPS group at the University of Amsterdam and working on smart search engines that learn directly from their users. Katja is the research lead of Project Malmo, which she's going to be talking about today, which uses Minecraft as an experimentation platform for developing intelligent technology. Without further ado, let's please give a hearty welcome to one of my, oh, well, let's not. Let's.
Oh, it's just a laptop. Oh, I see. Okay, that works.
I'll just pretend that was intentional. Very good. All right, please, let's give an applause for Katja.
Thank you so much to the organizers for inviting me to give the talk here. I'm especially invited to be here this year because it's such an exciting time to be doing research in artificial intelligence and in interactive and digital entertainment. So in the talk, I want to reflect on this a little bit. First of all, I will talk about the rapid advances in AI that we've been seeing over the past years. A lot of those advances were fueled by games, and I strongly believe that future advances will continue to be fueled by games as well. And I will spend a large part of my talk examining how games can be a catalyst for research in artificial intelligence, and I specifically focus on the Malmo platform developed in my team. Finally, I want to look at opportunities, especially in collaborative AI. And I think that the community here especially has a big role to play in seizing on some of those opportunities that come out of new AI technology and understand how that can lead to new game experiences. So let me start by reflecting on the advances in AI. We have certainly come a very long way since Alan Turing started to ask whether machines could be built that can think, that have human abilities or abilities that were thought to be uniquely human. And he argued in 1951 that in principle the brain can be understood as a computer and a computer can be understood as a brain. And therefore it should be possible to eventually develop machines that can think, that are intelligent. Since then, researchers in AI and related areas have developed a huge variety of systems that try to emulate abilities that were previously thought to be uniquely human. So over the past 60-odd years, we have seen the development of machines that can see. Maybe a machine wouldn't be able to know that this is a picture of some of the people in my team, that it was taken earlier this year, but the technology to detect faces is now integrated in every single mobile phone, and it helps us take that perfect picture of our friends. Speaking natural human language was long thought to be a uniquely defining human ability, but there are now systems like Skype Translator that understand spoken natural language and translate it to a different language in real time, allowing communication across language barriers. We live in a time where things that were thought to be impossible only 5-10 years ago are now very rapidly progressing, and we're seeing new and new systems coming up that match or even outpace human abilities. Of course, we don't know that counting and computing is something that computers are exceedingly good at, but we now also see machines that remember, see, speak, walk, that make plans. And there's no end in sight to this development. We will see new technology coming out over the years. At the same time, there are unique challenges still. Each of those machines, each of those systems that I mentioned, only cover a very thin slice of what the whole of human ability is. And there are key challenges in understanding whether and how we will be able to develop machines that act altogether intelligent in interaction with complex, uncertain, and changing environments like humans do. So to address these key challenges, the research community will continue to rely on experimentation environments, and games are one prime example of an excellent experimentation environment. A key reason for that is that the next set of challenges in AI are around interaction. We are at a stage where, for example, computer vision is to a large degree solved. We understand how we can develop machines that recognize objects, mushrooms and dogs and faces, at the level of human performance. But the next generation of AI will start to move out of these thinly sliced custom-made systems, and it will move in the direction of systems that directly learn to interact with an environment. Now, interaction is key here, and interaction is key in games as well. And I think that is one of the key reasons why games are such an important area for doing AI research. One excellent example of this could be seen, of course, a few years ago. First of all, people developed an AI experimentation platform on top of an Atari simulator, opening up the wide range of Atari games for artificial intelligence research. And of course, as you probably know, this formed one basis for the groundbreaking results by Me et al. From DeepMind, published in Nature in 2015, where they showed that a single deep reinforcement learning architecture was able to learn to perform at or above human level for at least 3/4 of those games. And at the moment, the performance is actually even higher than that. The key enablers to progress like this, to advances like this, are in my mind focused on those 4 areas that I'm showing here. Of course, you need algorithmic advances. So for example, in DQN, in the work of Nie and his colleagues, there were combinations of algorithmic advances that had been around for a long time, the idea of reinforcement learning, using function approximation for that, but there were key challenges, for example, in understanding how neural networks could be trained as function approximators without diverging. And there were key insights in how to make the training process stable enough using a target Q function, for example, that is updated at a much lower pace than the one that is being trained, that helped actually get those results. The second factor is compute. We have seen that some of the algorithmic advances were already developed many years ago, sometimes even decades ago. But we're now at a stage where computing power is big enough, has advanced enough, so that we can actually train those systems at scale. This is closely related to data. In order to train current, for example, deep learning architectures, massive amounts of data are required. And we now have both the ability to collect data at this scale, and we have the compute power to actually process it. Last but not least, it's crucial for any empirical discipline, and I see AI at its core as an empirical research discipline. The core of this is experimentation. So it's crucial that for rapid progress in an area, we are able to very rapidly implement and test new ideas and to measure progress towards a goal. This ability to rapidly test new ideas and measure progress is also something that is that is really inherent to games. And in fact, I find this aspect of the research so important that me and my team spent the past year or so developing a new experimentation platform for AI. And when we set out to do this, we set out to develop the ideal experimentation platform for artificial intelligence research. You may have heard about this. It was picked up by a huge range of news outlets. In the next couple of slides, I want to give you an idea of what the platform is about, why I think it's so well suited for AI research, and I'll give a demo that just demonstrates some of the abilities and what you can do with the platform. To give me an idea of the background of the audience, who of you has played Minecraft? Almost everyone. Okay, that's fantastic. So I don't need to explain much, just for the couple of people who haven't played it before. Minecraft is a sandbox game. It's open world. So a key distinguishing factor in Minecraft is that you can interact with everything that you see. You enter this world of voxels, and you can see some examples here. You can just roam around and look at the a square sun setting above the horizon. You can explore, you can build crazy structures. A lot of people play it socially, so they enter this world with their friends, go on adventures, create little puzzles or games with their friends or for their friends. But everything that you see in this environment, you can interact with. You can take every single block, you can destroy it, you can change it to something new. And this open-ended nature is what I'm particularly excited about, because it gives rise to an infinite variety of goals and tasks that people set out to do, and that we can translate into something that we can post to AIs. So this gives us the ability to create tasks within the game that start from the level of current AI algorithms. We can implement tasks that can easily be solved using current methods. But because this is open-ended, we can then take the same platform and increasingly make the tasks harder and harder. And that gives us a gradient for learning to increasingly develop smarter and smarter algorithms. And the moment they solve a task, we just go and we create a new one, and we make it harder for the AI. And that can really push the research in the direction of more and more complex interactions with this environment. In Minecraft, the 3D worlds are procedurally generated, so in principle they're infinite. Now, based on the platform, we can have both human and AI players experience this world from a first-person perspective. This allows us to easily generate large amounts of data, and the worlds reflect the complex physics that is, of course, not like real-world physics, but that is coherent and complex enough, I think, to drive a lot of research as well. Now, when we developed this platform, there were a couple of ingredients that were needed. We needed to easily connect AI agents into the game. We needed the ability to rapidly run experiments, to make experiments repeatable, benchmark algorithms, reproduce results, etc. Now, before explaining in more detail how we did this with this platform, I just wanted to show you this overview of characteristics of AGI environments, tasks, and agents that was posited by first Laird and Ray in 2010, and then extended by Adams and his colleagues in 2012. They posited to push towards more generally intelligent AI algorithms. We need to be able to experiment with environments that have complex structure and that allow for diverse interaction and structure. We think that Minecraft fits this bill because of its complexity, the richness of the structure, and the interactions provided by Minecraft. And the environment should be open and dynamic. Again, here we have a huge variety of open-ended worlds that can be created. There should be task-relevant regularities, and I think this is really important as we move towards, for example, multitask and transfer learning. If you understand the regularities of moving in a 3D environment, in a 3D space, there's a lot of information that you can transfer to a new task, and this gives us hope to develop agents that don't have to learn everything they know from scratch every time we give them a new task, but that can generalize and transfer knowledge as they experience, as they gather more experience in the world, and as they tackle new tasks or solve new problems. It's important that other agents impact performance, and the reason for that is that other agents impacting performance create a lot of complexity and change in the environment. This is why early on we support multi-agent scenarios, including scenarios where both AI and human agents interact with each other. We need to be able to support complex, diverse, and novel tasks, as well as complex interactions between tasks. We should reflect the limited computational resources that we have in real-world environments. There's some interesting connections here because there's a natural time limit if you want to interact in real time with a Minecraft environment and potentially with human agents in that environment. And finally, there should be the ability to have long-term continual existence of agents. And this area of long-term learning is something that is definitely supported in a game like Minecraft, but it's something that I think will take a while for researchers to actually address. Now, we took those characteristics and translated them into the Malmo, Project Malmo platform. We released this platform earlier this year, this summer. It's now on GitHub for everyone to try. And we already have hundreds of researchers and thousands of enthusiasts working with the platform, trying out what you can do with it, and also using it as the basis for their research. So we're hugely excited about the feedback that we've already gotten from the community, looking forward to hear more from people on how the platform fits with their research, or whether there could be extensions that would make it more suitable for the research that people have in mind. As I mentioned, it's on GitHub, so you can go and try this out today. But now, what is Project Malmo? What does it provide? I want to start with a few use cases and design principles that kind of guided the development. The use cases include that it needs to be really, really easy for any researcher to integrate their AI agent, their architecture, into the game. So we provide an intuitive yet powerful API for plugging in an agent as simply as possible. And I'll show an example of how that works in just a couple of slides. We need to provide researchers with tools for task creation. So although you can easily just drop an agent into a Minecraft world, in a lot of experiments, we need to create a task that is smaller and more repeatable than what would be provided by just having an agent roam around Minecraft and maybe trying to survive. So we provide a set of tools that allow people to create these tasks, define reward structures, elements in the environment, etc. It is built for extensions and novel uses. That's why we made the platform open source. It has a system of plug-and-play observation, command, and reward handlers. So if people want to work in a different observation space or a different action space, that is very easily possible using the platform. We also wanted to make sure that the entry barrier is as low as possible. So we created a system that is completely cross-language and cross-platform. So it runs on your Mac, Windows, or Linux laptop. You can implement agents in Java, .NET, C, C++, Python, Lua, etc. So hopefully that makes it as easy as possible and reduces entry barriers as much as possible. Now, the platform itself consists of a Minecraft mod that hooks into the game, and it exposes information about the current state of the world, and it provides information about observations and rewards to the agent, as well as listening to commands coming from the agent. On top of this, there's the platform Malmo API, so that's a library that you would typically import in your project, and this wraps the interaction between the mod and the agent. And finally, the user code plugs into this API. The user would define the task, the agent, and they are free to pick their experiment design or maybe use external resources as needed. The platform comes with a small set of example agents and tasks, and I'll show some of those here. So let's start with use case 1. We have just downloaded the platform, and we want to get a simple agent up and running. Key here is that all agents have to implement this basic interaction loop. So they observe some observation about the environment, they take an action, they get a reward. This is what a simple agent would look like in Python. We import the Malmo library, and the communication between agent and system is directed by the so-called agent host. Using the agent host, we start a mission. Mission is the term that we use for task here. And in this particular example, we'll just have a flat world with no goal. The basic interaction loop is implemented there, as you see. While the mission is running, we get a new world state. In this example here, we just ignore the state of the world, and we just tell the agent to move, turn, and jump. And sure enough, we get a moving, turning, and jumping agent in 2 minutes or less. This one is given in Python, but the code in Java or C++ would look very, very similar. So it's very easy to actually adapt this to the language or the system that you're already working with. Now, it's not enough to have an agent move and jump and turn around in an environment. So we also want to give them something to do. There are 2 ways in which we can create a task in the environment. And the one that is most developed, that we want to focus on, is using a mission XML. We decided to use an XML format because it's, again, independent of the programming language that is used to implement the agent. So this makes it really easy for someone to take a task or the mission XML that they use to run their experiments, give it to someone else, and this makes the experiments very repeatable. Now let's look at what this would look like. We have a simple XML format where we give some basic information about the environment. Key here are 3 sections. We need to define the initial conditions on the server, such as weather or elements that are present in the environment. We provide server handlers, so this says something about what information should be sent from the server to the agent. And finally, the key part there is the actual agent handlers, which define the observations or the state space for the agent, as well as the action space, and then the reward that the agent can obtain. So initial server conditions is pretty straightforward. We define a time, whether time should pass or not, whether mobs and creepers should spawn or not. And then we want to set up some basic environment. So what should this environment look like? In this example here, we just start from a flat world over there, and then we draw a couple of elements that define a room filled with lava and a platform on top. So you can see that here. For those who aren't as good at parsing XML, here's what this would look like in the end. So we have the agent over there, and the task here would be to actually walk to the end of the platform on this cliff. For those of you who are familiar with reinforcement learning, and maybe Sutton and Barto's book, this is a take on a classic reinforcement learning task, cliff walking, that is often used as kind of the starting point for figuring out whether your implementation of Q-learning is actually correct. Finally, we need an agent that interacts with this environment. Here we can define, as I mentioned, the observation space. Observation from full stats would provide information about the health, the life, server time, etc. We can provide video. We can provide more symbolic information, for example, about the grid of cubes that are currently surrounding the agent. So from here on, the researcher is free to work with different observation and action spaces. And I think this is one of the key advantages of the platform, because this allows us to compare, for example, approaches that make very different assumptions about what information about the environment is perceived by the agent. In this example here, the agent would move in a discrete fashion, so that means it just moves one block at a time. And finally, we define the reward structure. So here in this cliff walking task, we want to give a negative reward when the agent dies in lava, a positive reward when it reaches the goal, and we give a small negative reward on each individual step. And this very simple structure, this XML structure, gives rise to infinitely many AI challenges. We've designed the XML so that you can take as a starting point some Minecraft world that you might have created or just randomly generated. You add to it the observation and action space for the agent, as well as a reward structure, and you're ready to go and actually run an experiment. There are a lot of resources already available, for example, where the community gives information with troubleshooting or answering questions. But now I would like to give 2 examples to just show how Malmo can be used for reinforcement learning research. And I'm focusing on reinforcement learning here because it's such an important topic for developing agents that actually learn to interact with complex changing environments. So just in case you don't recall this right now, Reinforcement Learning 101, one of the most basic quantities in reinforcement learning are so-called Q values. So those are state action values. And the way I've written this here is under a given policy pi, the state action value of S and A is the expected discounted cumulative reward that is expected if I take action A and state S and then follow the policy pi after. And now key to Q learning, to actually learning this quantity, is the focus of Q learning. The idea is that an agent here interacts with an environment that is initially unknown. So it has to learn from trial and error what the consequences of its actions are and how it can maximize the Q values or the future expected returns of its actions. The key relationship here is the Q-learning update based on the Bellman equation. The idea is that we iteratively improve the estimates of the Q values. So we have the previous Q value over there. It's updated given via a learning rate. And the quantity that it's updated by is called the temporal difference error. And it consists of this relationship between our current estimates for ST and AT and the quantity that this should be equal to. So QST AT should be the same as the reward that we observe by taking action AT in state ST and then following the policy, the optimal policy after. So you can see that if this relationship, if this function had converged, this would be an identity. And the key in Q-learning is the realization that by iteratively updating the Q value estimates like this, we can actually converge to the optimal value function and to the optimal policy for the agent. Now I'll show two examples. In the first one, we will work with classic reinforcement learning, where the Q function is learned has a tabular form. So we'll go back to this cliff walking task that I show over here. And in this example here, the observations that the agent observes are tabular. It's just observing the number or the identity of the state that it's currently in. At each point in time, it has 4 actions available to move north, south, east, or west. And it has to learn from trial and error what action in what state actually leads to a positive outcome. So initially, if we run this in Malmo, the agent hasn't learned anything, so it dies in lava an awful lot. Let's see why that is. After we've initialized the agent, this is essentially what it's already learned. It doesn't know anything about its environment, and it has to explore the environment in order to learn about the consequences of its actions. So over there in the corner, you see the state that the agent starts on. Those red little circles indicate that it has learned that there is a negative consequence to taking that action in that state. And the neutral, or as they become more green, circles indicate that the agent has learned that there might be some positive outcome. Now, as we run this forward, we can see that the agent is continuously gathering more information, updating those Q values as it goes along, using the dynamic programming update that I showed earlier. And over time, it starts to get closer and closer to the goal, until after about 5 minutes of learning, it has found out that the goal is there in the top and that there is a safe way to get there. So using this simple classic formulation of reinforcement learning, we can get the agent to learn this in about 5 minutes to get to the goal successfully. Now, I want to contrast this with some experiments that we have done using, oh, by the way, I wanted to mention that this example here is provided with the Malmo platform. So if you go to the GitHub page, you download and install the platform, you can have this up and running on your machine within an hour at most. The next demo that I want to show is something we have just implemented over the summer. It's a team effort like all of the work that we do, but I wanted to highlight the contribution of 2 of my interns. First of all, Lydia Liu, who implemented and validated the deep reinforcement learning approach that we're using here, and also my current intern, Himanshu Sani, who came up with the idea of putting this demo together in order to let us better understand what a deep reinforcement learning algorithm has actually learned. So in this example here, all we will do is replace the tabular estimates, the tabular function approximation, the tabular approximation of the Q values by function approximation. So the Q value estimates are now learned using a deep neural net. And this is the approach shown by Mni et al. Here we're analyzing how this approach performs in this 3D scenario over here. So in this demo over here, there are 3 elements. On the down left on the screen, you'll just see the actions taken, the Q value estimates by the agent. In the top corner there, you can see the current knowledge of the agent. So you'll see the observed state. The top one is the current observation, and then we will have 4 history frames. So it'll be current t-1, t-2, t-3. And next to it, we see the current estimates of the Q values that the agent has. So you can see in this example here, the highest Q value is for moving forward. And then the large window is just an external view. Actually, there's a third-person observer in the same scene that allows us to see from a third-person perspective what the agent is actually doing in this environment. Now let's take a look. All right. We can see that this is an agent that has already learned to do the task. So this is really just for evaluating and understanding what the model has learned. And some things that are really interesting here are to see how the agent has, for example, learned to turn around to gather information in order to fill up its history buffer so that it has enough information to actually perform the task. And we can see this nicely in this example here. We could see that the agent repeatedly looked over to see whether the lava was still there until it had moved far enough to actually cross into the next. Let's see. Oops, I wanted to just show this again. All right. Were there any questions? All right. All right, unfortunately, it's playing only once. All right. So what makes this really interesting here is that we now have an environment where we can very quickly and easily understand what an agent has learned. And I think this would be one key aspect of making sure that we can develop tasks that are intuitively understandable, that reflect the real-world environments that we want to eventually move towards in a close enough way, while still being easy and controlled enough to allow for very rapid experimentation. Now, in the last part of my talk, I would like to reflect on some opportunities that AI and games create in this space. The current approaches in, for example, deep reinforcement learning are still quite slow, and it will take some time before they can actually learn fast enough to learn to interact with complex changing environments. Some of the research directions are, for example, to expand reinforcement learning, of course, integrate deep learning. We've already seen huge advantages to that. Integrate things like reasoning and language. So there's a hugely exciting area of research direction on the AI side. But I think there's also a huge opportunity in understanding how this will lead to new interactive experiences. And one area here is that I'm particularly excited about is the area of collaborative AI. So coming up with algorithms that can learn to interact with not just this 3D physical environment, but also human or other agents that the agent might encounter in this environment. There are some key questions posed by that. And I want to just emphasize that the type of AI approaches that we're now seeing developing will eventually give rise to new interaction paradigms between humans and AIs. At the moment, a lot of the interaction that we build into systems is hard-coded, scripted. But what we're seeing now is development towards agents that can actually learn in real time how to interact effectively with complex changing environments. And a key part of those complex changing environments will, of course, be people. There's a key challenge here to the research community, especially in aid. At the moment, we don't know what these interactive new experiences will look like. And in contrast to what a lot of Hollywood movies assume, the best shape behavior and appearance for an intelligent agent that interacts with people may not necessarily be the looks and the appearance and the behavior of another human. But at the same time, we are moving towards systems that are not entirely like the machines we know today anymore. We will move away from systems that are just hard-coded to do the same thing every time. We will move towards systems that are ever so slightly more intelligent than the machines that we know today. So what kinds of new metaphors can we come up with? What kinds of new systems or experiences can we design that communicate appropriately what the ability of those agents are? For example, one metaphor could be based on pets. For example, dogs and cats have been part of our environment for millions of years. We know that they are intelligent in their own right, but they're nothing like another human being. So maybe this could provide an interesting metaphor for how we will eventually interact with systems that are not human, not animal, but that are intelligent as well. Or maybe we will come up with something that is entirely different. For example, here, one of my favorite characters, my neighbor Totoro, from the Miyazaki movies. It's not human, it's not animal, it's a magical creature that is nevertheless very engaging, very relatable, and it provides an engaging new interaction with some mystical environment. So a couple of key questions that I would like to leave you with are shown in this slide here. First of all, what appearance and what kind of behavior in the future AI systems that we develop can lead to intuitive and engaging interactions? Also, how can we convey what those new characters can do and what they cannot do? For example, if we have systems or agents that learn from what we demonstrate, that learn from interactions with us, what does that mean? How quickly can they learn? What can they learn and what can they not learn? And how do I appropriately convey that in the interaction, in the behavior, and in the appearance of the agent? What are effective communication mechanisms? At the moment, a lot of interactions are based on human natural language, and the assumption is that eventually those agents will be perfect speakers of natural English, and that will be the most effective way to communicate. But maybe that's not the case. Maybe they can communicate using symbols or gestures that haven't been invented yet. And finally, what novel types of games could be uniquely enabled by the new AI technologies that are currently being developed? I think in this area, there's a key role for people in this research area to play in order to creatively explore the space of new AI technology and games and interactive digital entertainment in order to lead the way in creating new and engaging experiences around the new AI technology that is being developed. To conclude, I've started by reflecting on the very rapid advances in artificial intelligence and looked at how they're fueled in part by video games already today. I've argued that a lot of future progress will again be fueled by games, and they have key advantages in terms of repeatability, scale, the amount of data that we can collect in an interactive environment that is complex enough in order to push current technology, but also simple enough to allow for repeatable, controlled experimentation. Finally, I talked about some of the opportunities that are created by the new technology that is being developed. And I encourage you to think about the new experiences that this can enable. I look forward to hearing your ideas in the rest of the conference, and thank you very much for your attention.
So we have about 14 minutes for questions. So about observations, is it like the raw pixels of the things that agent is seeing?
Yeah, so as I mentioned, there are different observation handlers in the game. In the first example I showed, there was just a grid world observation, and in the second example, it was the video frames that were the observation. But there's a lot of space for plugging and trying out different kinds of observations there.
So how efficient would it be if we want to
Interesting. So you can, and absolutely the game runs faster there. So we are supporting overclocking, and the fastest you can run it is 1 millisecond per game tick, which is, I believe, a 50 times speed up over real-time game. There are types of experiments where the platform is not ideally suited. So if you really want to work strictly in a symbolic space, where you don't need the graphics, you don't need the extensive physics of Minecraft, then I think it would be overkill. So I think there's experiments where this is very well suited, especially where you want to compare agents using different observation spaces. It's not the fastest thing in the world that you can use for example, running toy examples.
So you mentioned with the grid world one, it took about 5 minutes.
Oh yeah.
With the other one that was like sort of pre-trained, like what sort of time scale is that at, and on sort of hardware?
So it takes about a day. That is about 1.5 million, 1.5 million frames, about a day on a Titan X GPU. Just for fun, I ran it on my desktop machine last week. It took the whole week, but it does converge eventually. Yep. No, it didn't. I could actually still use it to create these slides. So yeah.
You mentioned one sort of interesting thing about Minecraft is you can do interaction between these agents and humans. But to the best of my knowledge, Minecraft, sort of the primary way people interact is via text. I was wondering if you have any support for sort of social interactions beyond that.
Yeah, so there are two main ways to interact. One is the text chat. The other one is actually using the visual space, so using gestures and actions in the environment. So, for example, within the Minecraft community, some gestures have quickly evolved. For example, you can duck, and people created this kind of greeting very quickly that you can use from just using gestures. So there, in real world environments, we don't use just language. We use gestures. We use the environment in order to communicate our ideas. And this is possible in the Minecraft world, albeit in a simpler, slightly more structured way than you have in the real world. I see a lot of questions. Let's start in the back, maybe.
Do you have any reports of this platform being used for teaching? Because it seems that the students would engage a lot with it, because it's a lot of fun.
Yeah, that's absolutely a question that we get a lot. I know from some educators at universities that are already using the platform in their courses, for example, to teach about introductory AI concepts. There's a lot of interest in using it for programming. We have high school students who use the platform who just enjoy coding and trying things out. There's one person that I've recently interacted with, and he's enjoying changing our tutorials that are mostly in Python at the moment and coding them up in Java. So there's a huge number of different ways in which people engage with the platform. Yeah.
Do you have any plans, or have you thought about having agents that can consume data from outside of the Minecraft world, maybe through external sensors or questionnaires, or is there any notion of that?
I think that's absolutely possible. It would be part of the agent design, so it's not something that we're explicitly supporting in a way. But because you can plug in whatever agent architecture you have in whatever language you coded it up in, there's, you can really just use this as a provider of video images, for example, but use all the other data that you're already working with. I think that's a really good question. Whether or to what degree we can transfer what we've learned in this platform to other environments. Obviously, the visuals would be very different in a different environment. So you wouldn't necessarily be able to take a trained model from this and transfer it to anywhere else. what I do think is transferable are the learnings that we take of this. So for example, understanding here in the example that I showed how the agent is using the history frames and how it's collecting information to make sure it has the right information in its visual buffer, that is something that can definitely transfer to a larger range of settings. And I hope that the platform here makes it just easy enough to really push forward in understanding how agents collect information, how they can as efficiently as possible learn to interact with an environment, and then we can take those learnings, those algorithms, and transfer those to other games in the beginning, and eventually also to real life settings. Yeah.
You showed some examples with a single agent. I'm wondering if it's relatively straightforward to extend this to multiple agents, if we're just putting more tasks in the XML file, or if there's sort of explicit support for that, or how you see that scaling.
Right. So we are explicitly providing support for multi-agent missions already as part of the platform. There are a few caveats. It's not as well tested as the single agent tasks, simply because we or other people haven't as extensively worked on multi-agent scenarios so much. In terms of scale, the platform currently requires logins for multi-agent missions. So it's reasonable to run maybe 2 or 5 agents, but scaling this to 100 of agents is not currently feasible. It uses a network connection, so that is the reason that I wasn't showing the demo here live. The one where you saw the agent from a third-person perspective actually has a human observer that is already in the environment. I'm happy to show that off later on when the network connection is reliable. Yeah.
So in addition to the affordances for hooking into agents in the environment, what affordances does the project have for maybe controlling the generation of the environment itself?
So we have a couple of mission generators that are provided kind of as examples for how you would create much more complex environments. So for example, there's a classroom decorator that creates a kind of sequence of increasingly complex dungeons that the agent has to navigate. So there is an API through which you can interact with the environment, so you can use that to create new tasks, task generators. If something becomes very complex, there might be a way, it might be necessary to hook that into the platform, but then you could follow the examples that are already in there. Yeah. We are trying, with the mission XML, we're trying to, as much as possible, rely on the things that are already provided in Minecraft. So for example, using redstone, you can create machines, you can create mechanisms that the agent can interact with, or create puzzles where you have to activate a button in order to solve it, things like that. I think there's a huge amount of space there as well. So there's definitely an interesting space to both explore how to generate tasks, but also how to use what's already provided within Minecraft for interesting new kinds of tasks.
We've got time for 1 or 2 more.
So I have one question. I was wondering, so in the collaborative AI realm, I was wondering what opportunities you guys are looking at for more creative tasks, like designing a castle together, or making designing a game, or like those really open-ended kind of weird problems.
So we had, it's an area that I absolutely want to look into more. I think we're just barely scratching the surface of what's possible there. Over the summer, we had one intern project that looked, the intern is a social scientist, and he looked at how it would be fun or interesting to engage with the AI agents. And in that experiment, we were using Wizard of Oz setups. So a person was supposed to act as an AI and help the kids using a creative building task. So they were supposed to build a maze or something like that. It was really interesting how different people interacted in different ways with the agents. And our key learning was that we probably need to structure the interaction more or scaffold it more and provide more information on what it is that the agent can or cannot do. Because some kids were approaching it like, oh, it's like a human. And they were trying to go out on adventures, and at some point the Wizard of Oz was just scratching their head. It's like, there's no way an AI would be able to do this. So they just had to stick to a more structured kind of interaction. And others were using it strictly as a machine. So for example, they would figure out that they could get the agent to mine wood, and then bring that, and it would just like, okay, mine more wood. And then for the person doing it, it was mind-numbingly boring because you just had to go back and forth and get more materials. And I think there's a huge space in between where an AI agent doesn't have to be human-level intelligent, but it can be slightly better than just a machine where you push a button and you get a toast or something like that. And I don't know what exactly the right models are to think about this. I think it is a huge creative task. In some movies and in some existing computer games, there might be models that we can already use as a starting point. But I really don't know what's going to be possible using these more intelligent agents, more interactive, more adaptive environments. Absolutely, I'd love to talk about this more.
Time for one more? Or?
That's funny you mentioned that. It's something that I just started thinking about recently, and trying to come up with kind of simple games between the AI and the human that would be fun to play. I haven't thought exactly on the specific details of how you would implement it, but it's absolutely possible, and I think that could create some really interesting dynamics between human and AI agent.
All right, well, so let's thank our